In this video, we will explain complex numbers. We can think of complex numbers of numbers that can be written like x plus iy, where x and y are real numbers. Notice that there is a very natural identification with a complex number and points in the plane, points in R2. For example, if we have 3 plus 2i, we can think of this point 1, 2, 3, 1 and 2, then we can think about this part, right? And essentially, we're going to be calling the x, when you have a complex number like this, the x, which is a real number, we're going to be calling it the real part of, let's call this the complex number c, real part of c, and it's going to be denoted as re of c, and the y without the I, right? The y is going to be called the imaginary part of c, and it's going to be denoted Im of c. We have an operation. We can do two operations here. The sum of complex numbers is just the regular sum of vectors. When you think of here, it would be like the regular sum of vectors, or it would be just like pretending that I is a variable and then you just add. Let's say if you have z equal 2 plus 3i, and then you have w equal 4 minus 2i, then you just add, pretending that I is a variable. Then you have 2 plus 3i plus 4 minus 2i. Then this is just 6 minus 6 plus i, right? That's the sum. And the interpretation is that if you have this is c and this is w, then the sum, to do the sum, you just move this vector so that it starts here, and then wherever it ends, then this is c plus w. That's the interpretation for the sum of two complex numbers. And for the product, we have that we do the product just by pretending that I is a variable, but then with the rule that anytime we have an I square, we're going to change it to -1. Then that's the only thing that you have to do. Then if you want to multiply these two, it will be 2 plus 3i times 4 minus 2i. And then when I do the product, I just pretend that this I is like an x or a variable. And then you do 2 times 4 is 8. Minus 4i plus 12i minus 6i squared. And the rule is that anytime you see an I squared, you're going to change it with -1, and then you have 8 minus 4i plus 12i. Or I can combine these two because they are like terms. Then I will have plus 8i, and then plus 6 because this is a -1, and then we end up with 14 plus 8i. What is the interpretation for the product? Let's just do this pair here. Let's see if I can't. Oh, okay, let's see, what can I do? Let's suppose that we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here we have -1, -2, -3, -4, -5. Then the vector c would be 1, 2 plus 3i, 1, 2, 3. It would be just here, 2 and 3i. This is c. And w is 4 minus 2i, 1, 2, 3, 4 minus 2i. It would be here, right? And then the idea is to explain where is this product. This is C times W. What is that product? Then in order to understand that, we think about the length of the vector C. By doing the Pythagorean theorem, this is 2, one leg is 2, the other leg is 3, then this is a square root of 2 squared is 4, plus 3 squared is 9. The length of this is a square root of 13. What is the length of this vector W, of this complex number W? By the same reason, this leg is 4, then it's a square root of 16, and this is 2 squared will be 4, this is a square root of 20. We can see that the product, the length of the product is the product of the two lengths, right? This is a square root of 13 and this is a square root of 20. Then you can check that this is going to be the length of this vector, of this complex number, is going to be a square root of 13 times a square root of 20. And I just leave it as an exercise that this is the same as a square root of 14 squared plus 8 squared, right? By the Pythagorean theorem, we know that the length is this, but you can check that this is equal to this product. But then we know the length, right? But then with this length, there are like infinitely many possibilities. How to catch which complex number with this length is the one that is the product of these two. In order to do that, we can think about this angle here. This angle, let's call this angle theta 1. We can think of a positive angle. We can think about polar coordinates 2. And let's think about this angle theta 2. Then, when you add these two vectors, notice that here when you add these two arguments, these two angles, theta 1 and theta 2, maybe theta 1 is a little bigger than theta 2, then you will have a positive angle. Then here you will get, when you think about this 14 plus 8w, 14 plus 8w, maybe here 1, 2, 3, 4, 5, 6, 7, 8, right? Maybe here, this is the product CW, which is 14 plus 8i. This angle is going to be the angle theta 1 plus theta 2. Notice that here theta 1 is positive, theta 2 is negative, and for that reason it's a little bit smaller. We have that interpretation for the product of two complex numbers, but remember the product is very easy to do. You just do it like if pretending that I is a variable, and anytime you see the I square, you replace it with negative 1. Okay, we have that. Let's just practice this interpretation. What happened if I have this I? What is I times I? I times I is negative 1. But why is that? What is the length of I? The length of this vector is 1. And what is the argument? Theta 1 equal 90. How do you do I times I? Length 1 and length 1 will give you something of length 1. And what is the new angle? 90 plus 90 is 180. For that reason, that's the reason why I squared is equal to negative 1. There is a good annotation that is going to be very important, and it's this, e to the I theta. This e to the I theta is going to be equal to cosine of theta plus I sine of theta. Notice that essentially when I write this, I'm writing a complex number. What is the length? When you think about the length, you're thinking about cosine squared plus sine squared. You're thinking about something of length 1. And when you think about what is the angle, you are thinking about exactly this complex number, e to the I theta. Then if I multiply, you can check that if you multiply e to the I theta with e to the I phi, cosine of phi plus I sine of phi, according to our definition of product, we will get something of length. This is something of length 1 and this is something of length 1. Then when you multiply the two of them, you will get something of length 1 as well. then it's going to be in the circle. And what is going to be the angle? This has angle theta, this has angle phi. Then you, if this is phi, this is e to the I phi, then you will be getting this. And you will get getting e to the I theta plus phi. We can actually check this when we do the product. E to the I theta times e to the I phi is equal to, when I multiply these two, I get cosine of theta times cosine of phi, and then I get plus I cosine of theta times sine of phi, and then I get plus I sine of theta cosine of phi, and then plus I square sine of theta sine of phi. But this is equal to -1, right? Then I can write this as cosine of theta cosine of phi minus sine of theta sine of phi plus I times cosine of theta sine of phi plus sine of theta cosine of phi. And you can check, if you remember your basic trigonometric identities, this is the formula for cosine of theta plus phi, and this part here is the formula for sine of theta plus phi. Then we have proved that that property holds true. I think that I would like to stop here about this complex number, and we will be having another video on complex numbers. Okay, let's stop here.